Welcome to another video explaining the universe using the particle model. Today's video is titled TPM Equations, specifically covering gravity 1 and gravity 2. I've been going through certain words. Previous ones were around light, waves, time and space. Now this is gravity. My next one will be on equations for circuits. I keep pushing off the vertical antenna because I'm having difficulty with the concept of a resonance. I mean, I understand resonance in a circuit sense. However, in the physical way that it appears to be talked about by ham people, could use some help here. Anybody who's a ham operator understands what antenna resonance is would be helpful. You can email me at particleguru@gmail.com. Now, there are several videos, more than this, but these two in particular cover equations, and so you may want to take the time, if you're interested, to watch the video titled Gravity is Not Free. That's the title of my book, which is not really released. It's a different book than Dave and I are working on, and in part 2 of that book, I talk about the experiment that Dave and I did to show that gravity was caused by a particle. And then I also did one on Majorana's experiments, where I actually did some calculations to calculate the values of the equation, which we'll be talking about. We'll talk about the terms, but not their values. So let's start with Newton's universal law of gravitation. And the reason I'm doing that is that it is the empirical form of TPM's equation for gravity 1. And of course, from Wikipedia, this is a statement pretty close to what Newton has said. Every particle attracts. He doesn't call push or pull. He says attracts every other particle in the universe with a force that is directly proportional to the product of their masses, m1 and m2, and inversely proportional to the square of the distance between their centers. That's his equation. I actually have derived his equation my own way, and I thought you might be interested to see that. He starts with his second principle, F equals ma. There's an equation I got from my physics book, which is a condition for circular orbit that says the acceleration of the orbiting object, the force of acceleration, pushing it towards the central object, if that acceleration is equal to the square of the velocity divided by the distance, then it will orbit in a circular path. And here's the orbital velocity. Picking up v from there is the circumference divided by time, or the period. And the key one is Kepler's third law. Kepler's third law for an elliptical orbit states that the period of the orbit, the square of the period of the orbit, is proportional to the cube of the semi-major axis. Elliptical orbits has two axes, a minor and major axis. And then finally, Newton inserts his own assumption that the force on the object is not only proportional to the larger object. So the first step is you take F equals ma and you plug in for a, you plug in v squared over r and you get mv squared over r. Second step is to solve this equation for t. You just switch the t and the v and you get 2 pi r over v is equal to the time. And then I repeat those first two steps, and then you take Kepler's third law and you replace t squared with the square of t, and that's 4 pi squared r squared over v squared. And in this case, again, in the red part, you solve for v squared by switching v squared and r squared, and you get v squared is proportional 4 pi squared r squared over r cubed. R, you cancel out the r squared, it leaves r in the denominator. So the final, or the fourth step, is to take this top one, and you replace the v squared with 4 pi squared over r, 4 pi squared over r. So you have m times v squared over r there, over this r, and then there's an r here. That's a small r there, and you get 4 pi squared m over r squared. Well, this is a proportionality, and this is a constant, and you expect to replace that with a combined constant for a gravitational constant. So you just drop the 4 pi squared, and you get force equals mass over r squared. But the force is, his assumption is that the larger the central mass, the greater the force. And so it must also be proportional to the large mass times the small mass. I go through all that for a specific reason. I don't want to labor with those who don't like math to struggle through that. But here's the point. Newton takes the elliptical proportionality, Kepler's third principle, and converts it to circles. So if this was accurate, then this is an approximation. Maybe that's not so accurate, and if it's not accurate in the first place, it's even worse. Newton assumes that objects must be perfect spheres, or at least contain concentric shells that all have homogeneous mass. There's a big assumption there. The objects have to be very precise. And the mass is concentrated at a point in the center. He states the r square is from center to center. So all the mass is assumed to be located in the center. That's a big assumption. And so I can make the argument that his equation isn't precise, and we'll go into that a little bit later. Well, that's how Newton did it. This is how I developed an equation for gravity 1 using Lesage's model. Of course, he states that streams of tiny unseen particles, which Lesage called ultramundane corpuscles, impacting material objects from all directions. And this is his hand drawing of two objects being imposed, not in all directions, but in this direction and that direction. So I have here, I'm assuming 100 particles coming in this way, and 100 this way, 100 this way, and 100 this way, really implying those are the ones coming right through the center. Just put the numbers up here. 100 come in, I lose 10%, I'm left with 90. 10 hit and scatter. Then I lose 10% again, 9 hit and scatter. I'm left with 81 at the surface. 100 opposing 81 gives me 19 more pushing this way than is coming out pushing that way. Same thing happens the other direction. You start with 100, you lose 10, you got 90, you lose 9, you got 81, you have 19 pushing this way on the surface. That's what these numbers are for. They're not center to center. They're, the way I did this, there's edge to edge. And notice, and this is pretty well understood, that when two objects always have the same amount of force pushing together. Okay, so then I take this this is a one-body equation, and now I change my 100 to n, and here's another n, so I'm taking this path, and I'm going to say that there's going to be, this particle is going to pass through this path, and it's going to lose a number. So it's going to lose a certain percentage, and I call that percentage P. And it's related to the mass in this path, the mass from this point to this point, both in this case, I'm showing it two-dimensionally, but the percentage loss is equal to the interaction factor times the mass. And what I'm saying is proportional to the mass, and I need a constant of proportionality, and it's called the interaction factor. What percent is going to interact? That's the whole thing. And so you have n coming in, you lose n minus p going through, and you have n opposing. So there's the n opposing this way, and this is n minus this, which is that expression, and that all reduces to a very simple n times PE. Okay, and then you want to find the force in the x direction. You can actually calculate the force in the y direction, and if it's three-dimensional, you can do z. But each particle applies a force of F sub I. I'm taking this n per b, which is my basic equation. Each particle applies a force of F sub I. That's the average force. It isn't constant. This isn't an absolute number. Sometimes it'll apply more, sometimes it'll apply less. This is the average force per particle, and the percent applied is going to be a PE, which is this formula. And if you want the x direction, you got to take the cosine of this angle for this direction, and you got to take the cosine of this angle for this direction. But in reality, if you're going to get the whole answer, you've got to go all the way around all angles. And this assumes 1 degree steps. I'm taking angle 1 to 180. This is the basic equation I just derived, and this is the supporting equation for what PE is. And this is a two-dimensional equation for exactly solving the picture I just showed you. To do 3 dimensions, you've got to start with a plane, do all the angles in a plane, pick another plane, do all the angles in the plane, and go all the way around 180 planes, and you will do a 3-dimensional calculation. So these are this is gravity 1 equation for the x direction. If you want the y and the z, you've got to add more sine and cosine terms to get the right proportion. Notice there is no r squared in my equation. Although when you do the calculation of the mass in that path, you're using geometry, and r squared indirectly appears, but it's not explicit in this equation. There is no g. What I have is the interaction factor is one virtual constant, and F sub 1 is the average force. That's another virtual constant. And so no r, no g. I have these two. Well, there's actually there is another term that falls out of calculations. I'm going to explain to you something I did when I was actually calculating g, small g. I assumed values for IF1, the interaction factor, and repeatedly adjusted F1 to get the right value, because I don't know what they are. I pick one, adjust, get the right value. Everything went well until I got to a high altitude, and then my answers jumped around. I tried to adjust and it would go high, tried to adjust again and go really low, high, low, and I said, wait a minute, what I need are more planes or more angles. So I increased the number of angles and planes by 5. Well, one or the other, I can't remember which. But I increased it by 5, and it stabilized my result. But when I adjusted Fi to get the right answer, it turns out I decreased F by 5. I increased the number of paths by 5, I get a decrease in F. So if I increase the plane by 5, F1 decreases. If I increase the angle by 5, F1 decreases. Told me, said, Bob, this term, PA, the number of planes times the number of angles in the planes, the total number of paths, and when you change this up or down, this is going to change accordingly. This is another virtual constant. Call this the potential force of gravity, gravity 1, at any point in space. This is F1 is the force of gravity of the G1 particle as it applies to the objects. Okay, well, I was actually solving for G, and it's a simple, this is just a repeat of the picture, and you take the force in the x direction, divide by 1 kilogram. I'm using the MKS system. So you divide by 1 kilogram and you get the value for G at any point. I was calculating the value of G going higher and higher. So that's very simple. You can calculate the value of Y, force in the Y direction, but that's like a horizontal force on you. As a side comment, because the Earth is an oblate spheroid, there is a sideward force on you towards the equator. Okay, so we've got the TPM equation. We've got Newton's equation, which is more accurate. He changes the ellipse to a circle to do the equation. The objects must be homogeneous spheres. Mass must be in the center of the object. If the equation is approximate, then G cannot be a universal constant. In fact, when I talked about dark matter versus G, it clearly shows that if you're going to use Newton's equation, the value, to get the right velocity of the stars, you've got to change the value of G. But in the TPM equation, F1 is the statistical average force of the G1. Hopefully that turns out to be a reasonable constant, but possibly not absolute. I sub F is not an independent variable. It is not an absolute. I already know from other work that I've done, it is that I sub F could be dependent on temperature and the speed of the G1 particle. But here's the big one. Mass distribution is accounted for. You can do the calculation of the force and calculation of G using an oblate spheroid, and you will get a better answer. People who want to use Newton's equation don't want to go through that. The problem is the TPM equation forces you to do it that way, and you will get a more accurate answer. Okay, Coulombs equation. This is, I started with Newton's equation for gravity 1. Coulombs equation turns out to be equivalent to gravity 2, an empirical equation for gravity 2. Coulombs law, or Coulombs inverse square law, is an experimental law of physics that quantifies the amount of force between two stationary electrically charged particles. TPM doesn't agree with the fact that particles have charge, so this we don't agree with, but this is what Coulomb did. The electric force between charged bodies at rest is conventionally called electrostatic force or Coulomb force. The law was first discovered in 1785 by French physicist Charles Augustin de Coulomb, hence the name Coulomb for the force. So this is not static. I picked this for this way, but if these were two at rest, this is his equation. It's very similar. Most people who see this the first time, we all said this. Wow, that looks just like Newton's equation. But he has his. This is the charge. This has a charge of E. This has a charge of E. This would be E squared over R squared. R being the distance between this center and that center, and they had to develop a constant of proportionality, which they called K. This is an empirical equation for this force between two charged particles. I drew this as a hydrogen atom because I wanted to draw a equivalent hydrogen atom and showing how G2 gravity is the force that surrounds all of this and keeps the G1 in orbit around the N1. That is equivalent to the electron around the nucleus. And here it's in charge. We reject that. Here we have to have mass. It's not in grams. I've made this point on other videos. You can't measure the electron or the G1 particle using G1 gravity. It isn't a gravitation. They don't act gravitationally that way. So it's in mass, and we have to define a new standard, but the mass of the N1 times the mass of the G1 over R squared. The F2 force, that is the gravity 2 force. This would be the empirical equation for the TPM solution. But we have to be able to develop that same thing. Now, this is a little bit different drawing, but it's just like the one that Lesage did with 2 objects. Got n number coming in here. I lose n times Pn, where Pn is the percent lost. And what leaves is n times 1 minus Pn, and then you lose some more here due to this one. And so the difference between these two is n minus this. N minus this reduces very simply to n times the percent lost through the G1 particle and the percent lost through the N1 particle. Same buildup of simple, you lose so many and then you lose some more. Again, this is only, I'm not doing it from center to center, I'm doing it from edge to edge. You can do it from center to center, but it's more complicated. You got to count for this piece separately and this piece separately and this piece and that piece and so on. Yeah, things get more, it starts out simple, things get more complicated the more accurate you want to be. So you end up with 2 and 3-dimensional equations, just like this is almost exactly identical to the other ones I showed you, but this is F2. That's the average force that the G2 particle applies when it hits the N1 or the G1. And this is the 3-dimensional version. You just add 180 planes with 180 paths. The reason there's only 180 paths in there is because this equation, P, I'm pointing the wrong way, this NPG is actually the sum of 2. So I've already got 2 opposing ones, so you only need 180. Same thing, no R squared. Yes, it's part of the geometry. There's no G, we have these 2 constants, integrate the interaction factor for the G2 particle. It's a different name here because it's a different level gravity. And F2 is the instantaneous force of the G2 particle when it hits the object. And these are the supporting equations. Well, that was a lot. I apologize to you, those who don't like equations, but I was asked by one of the viewers to talk about equations. I'm going to talk about circuit equations next, and you'll see. It's all the same. The base equations are going to be the same as before, as gravity, whether it's circuits or gravities, but it's handled a little bit different. If you have a question, ask Particle. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.